All right, Math 5130. This video starts the presentation of logistic regression, and we need to revisit an old buddy. One I think that one didn't go over that great, but it's just what it is. Called odds ratio. Now let's pump the brakes a little bit and review odds ratio. So if we're examining the relationship between a fall being reported dichotomously coded, either yes or no, and the use of a cane, dichotomously coded either yes or no, we can calculate the odds ratio, which would be, or we can manipulate, form the problem however we want. But what I want to focus on is the odds of falling when using a cane divided by the odds of falling when not using a cane. So since we have an odds divided by an odds, we call that an odds ratio. Well, the odds of falling when using a cane, I would focus on the cane line. So the odds of falling would be the number of people who fell, 35, versus the number of people who didn't fall, 40, so 35 divided by 40. The odds of falling when not using a cane, so focus on the not using a cane line, would be the count of those falling divided by the count of those not falling, 66 over 103. Put this in your calculator, you get the odds ratio of 1.37, and the interpretation would be the odds of reporting a fall when using a cane are 1.37 times higher than the odds of reporting a fall when not using a cane. That's kind of opposite of what I would expect, because you would think that a cane would keep from, you minimize the effect of, or the possibility of falling, but maybe, I don't know, this is something that would be interesting to study. Maybe people who are more likely to fall understand that and use a cane, but I don't know. That would be something that I think would be super interesting to dive deeper and see what is up with that relationship. All right, gang, enter logistic regression. And the title regression, let's see if I can make that just a little bit clearer. The title regression should tell you that it's going to kind of remind you of what we did with simple linear regression and regression. It kind of does and it kind of doesn't. They're very similar, but they're also extremely different. Logistic regression has a dependent variable that is dichotomous. Dichotomous means that we have a categorical dependent variable with two levels. Now remember, multiple regression, the dependent variable had to be quantitative. Similar and well, actually exactly like multiple regression, logistic regression has independent variables slash predictors that can be quantitative or categorical. Now, if we have something in the simple linear regression case, we have a linear relation. The focus there would be to create a model in the form y hat equals b0 plus b1 that best fits that model. But you can see over here in the logistic regression, you know, over here this variable is quantitative, so I can take on all of these different measurements. In a dichotomous situation, the values can either be zeros or ones. So fitting this with a straight line would cause all kinds of problems with some of the assumptions. So what we do is we create it with something, or I should say we model it with what we call a logistic model. And the logistic model, again, I love this stuff. I'm sure you don't, so let's not go into it much. That's not the focus of this class. But the logistic model looks at e raised to the b0 plus b1. Same thing we got over here. We have these coefficients that we'll get from R or stack crunch, and e raised to this plus 1. You will never ever be required to use this. It just makes creates a foundation for what I'm going to show you on the next page. So on the next page, with a little bit of manipulation, we can take that one term, e to the b0 plus b1x, and see that it is nothing more than the probability of x divided by 1 minus the probability of x, which, if you recall, is nothing more than what? It's just the odds. So in R, if we take e and raise it to something, we would have exp to that something. So in other words, if I have 3.5 and I want to take e and raise it to the 3.5 in R, I would just type exp 3.5. So that's going to play an important role in understanding the coefficient estimates in our R output. So again, recall that the probability divided by 1 minus the probability is just the odds, and if we have two odds, we can create the odds ratio. Now, you might be thinking, what in the world is going on here? Why does that even matter? Well, let me illustrate something to you in R and StackCrunch. So let's say over here that we kind of shift gears and don't want to just look at the relationship between false status and cane use, but we want to predict false status from cane use. So predict false from cane use. So in that case, y is going to be false status, yes or no, and our x is going to be cane use. All right, so the first thing I have to understand is I'm dealing with two categorical variables, so I need to ensure that they are actually treated as categorical variables in R. So instead of typing out false status all caps, I'm just going to rename it as false, because I tend to make more typos. But so I'm accomplishing two things with that line. I'm forcing false status to be a factor, and so in other words, for R to recognize it as a categorical variable, and I'm renaming it something easier to type. Same logic here. All right, so I have false and cane. The next thing I need to do is set my reference category. So I'm just going to set false and use the relevel command that I used in a previous video. So I'm just going to do that with the variable false, and I want to set the reference equal to none. And cane, I want to reset the reference to no. Actually, it has to be exactly the same. Okay, so just a little bit of work when dealing with categorical variables in R. And when we move into StackCrunch, you're going to see that there's a little bit of work we have to do there with categorical dependent variables and predictors. So to run the model, we do something kind of similar, but instead of using an LM command, we use a GLM command, General Linear Model. But the variables are entered the same way. We want to take false and predict it from cane, but because it's a general, sorry, I can't type and speak, because it's a general, I really can't type and speak. Because it's a general linear model, we have to specify the family, the probability distribution that we're using to make those calculations. So all this has to be there. I had a student absolutely flipping out on me. He worked really, really late into the night when he took my regression class, working on his master's in math, and he kept forgetting to put this here, and he was emailing me at like 2 o'clock in the morning. I'm like, dude, I'm asleep. I can't help you. But he just forgot that, and he was just getting everything wrong. So for a logistic regression model, you must add the family equal binomial to the GLM command. All right. So from there, we're going to see something, the summary of the model. It's going to take an entire video for me to go over all of this information. I want to go through every bit, particle, and piece and let you know exactly what this stands for and what these estimates are and everything. But the purpose of this video is just to kind of get the ball rolling on interpreting a simple linear regression model. Now you can see from this coefficient output what I'm trying to teach you over here, right? Clear as mud. You're like, Dr. Darbro, there is no 1.37 there. Actually, there is a 1.37. If I take EXP that I discussed a little bit earlier and raise e to the estimate for Kane, you can see that I get my old buddy 1.37. That is precisely what a logistic regression model does for us. It finds the odds of falling given Kane use. So the interpretation of this estimate will be exactly what I presented right there. It's the odds of reporting a fall when using a Kane are 1.37 times higher than the odds of reporting a fall when not using a Kane. It's precisely that. Now, quantitative variables, we get back into that as X increases 1 unit. The odds are, but I'll show you that in due time. And also in interpretation, if I have more variables here other than just Kane, which we will, you would add controlling for, just as we've done in the multiple regression setting. Okay?